Welcome to GNANA DEEKSHA, concept-based digital learning. I am Mallareddy, JL in Chemistry, TSWREIS Jagadgirigutta, Medchal district. So, you know already, haloalkanes, haloarenes and their preparations and properties. In the part of properties of haloalkanes and haloarenes, today we are going to discuss about nucleophilic substitution reactions. In nucleophilic substitution reactions, we have two types of nucleophilic substitution reactions here, that is SN1 and SN2. So first we see what is a organic chemical reaction. In that, first we observe a nucleophile is treated with alkyl halide, that is gives product and halide ion. So in this, alkyl halide is a substrate and nucleophile is a reagent. So when a reagent is being attacked to the alkyl halide or substrate, we will get product. So that is alkyl, that is R and nucleophile and halide ion. Here, a nucleophile, a species with an unshared electron pair or lone pair of electrons, reacts with an alkyl halide, that is substrate, by replacing the halogen substituent. Halogen substituent, here it is a leaving group. So in nucleophilic substitution reactions, the carbon halogen bond of the substrate undergoes heterolysis, and the lone pair electrons of the nucleophile is used to form a new bond to the carbon atom. So a nucleophile, here a nucleophile is a leaving group. So a nucleophile having more electrons, and in carbon halogen bond, so in a carbon gets positive charge and halogen gets negative charge. Heterolysis taken place. So a nucleophile is an negative ion or a neutral molecule that has at least one unshared electron pair. General reaction for nucleophilic substitution of an alkyl halide by hydroxide ion. See here, a nucleophile, that is hydroxide ion, having two lone pair of electrons and a negative charge. That's why it have three lone pair of electrons. That hydroxide ion is treated as here nucleophile. So that is being attacked to alkyl halide, that is alkyl group, or is attached to a halogen X. So that X is a halogen having three lone pairs of electrons, and we will get alcohol and a leaving group, that is a halogen, that is halide ion, having four lone pairs. Yes. So to be a good leaving group, the substituent must be able to leave as relatively stable, weakly basic molecule or ion. So in alkyl halides, the leaving group is the halogen substituent. It leaves as halide ion. So generally, alkyl halide leaving group is halogen substituent. So because halide ions are negatively stable and very weak bases. Halide ions are very relatively stable and very weak bases. They are good leaving groups. So here in nucleophilic substitution reaction, first we are going to discuss an SN2 reaction. So what is SN2 reaction? Here we are going to discuss. Children, the rate of reaction depends on the concentration of methyl chloride and the concentration of hydroxide ion. See here, the rate of reaction depends on both one methyl chloride and the concentration of hydroxide ion. Methyl chloride is a substrate and hydroxide ion is a nucleophile. See here, the reaction is second order overall. So the rate of reaction depends upon both substrate as well as nucleophile. See, the reaction is first order with respect to methyl chloride and first order with respect to hydroxide ion. I already told you that here methyl chloride is a substrate and hydroxide ion is a nucleophile. So the rate is directly proportional to the concentration of methyl chloride and concentration of hydroxide ion. Then rate is equal to the K into methyl chloride CH3Cl concentration into hydroxide ion concentration. Here K is the rate constant. So rate is directly proportional to the concentration of methyl chloride and concentration of hydroxide ion. So rate here 2. That's why it is a bimolecular nucleophilic substitution reaction. So the molecule attacks the carbon bearing the leaving group from the back side. See here, nucleophile is attached behind or back side of the leaving group. That is, here the bond between the nucleophile and the carbon atom is forming, and the bond between the carbon atom and the leaving group is breaking. So in front side bond is breaking, back side bond is forming. So the configuration of the carbon atom becomes inverted during SN2 reaction. So configuration will be inverted because bond formation and bond breaking occur simultaneously in single transition state. So you know here transition state is formed. Transition state is more unstable, and the SN2 reaction is a concerted reaction. So in transition state, see here, this is the mechanism of SN2 reaction, children. The hydroxide ion is attacking backside of the alkyl halide, and the leaving group, that is halogen, is leaves from the front side. So in transition state, you see in middle transition state, in that the chloride ion is leaving and hydroxide ion is being attacking. That's why the final product we will get methyl alcohol and chloride ion. What happens here? Inversion takes place. Inversion takes place. See, this is the free energy diagram of an SN2 reaction. So reactants in that substrate YZ and nucleophile X minus. The free energy changes from delta G to delta G naught. So delta G plus, that is transition state. When we give some energy, transition state is formed, and after transition state, immediately it is converted into product XY plus Z minus. So this is the free energy diagram of second order, that is SN2 reaction. See the methyl alcohol formation. So next, so for methanol, you see, so this is the free energy diagram, how methanol is formed in SN2 reaction mechanism. See, OH, hydroxide ion is being attacked to methyl chloride from backside. So we will get transition state in the middle, and finally we will get methyl alcohol and chloride ion as a product. So this is the free energy diagram of for methanol in SN2 mechanism. Yes. So you see stereochemistry, how inversion takes place. So hydroxide ion here, see, attacking backside of the methyl chloride, and chloride ion is leaving from the front side. So you see transition state is more unstable form, and finally we will get inverted methyl alcohol and halide ion. So an inversion of configuration you observed here clearly. Then see reactions of alkyl halides, SN1 and SN2 reactions. Reactions of alkyl halides, you see methyl fluoride, methyl chloride, methyl bromide and methyl iodide. So how they carbon and halogen electronegativity difference, here you observed here the methyl chloride in methyl carbon fluorine electronegativity difference is 4 minus 2.5, we will get 1.5. The electronegativity difference is more in methyl fluoride. Then you see methyl chloride, that is 3 minus 2.5. Carbon is here methyl is 3 and you will get just 0.5. And then in methyl bromide you will get just difference is 0.3. But in methyl iodide you will get 0. Both are 2.5 and 2.5. So the carbon and alkyl halide is electrophilic. So electron for either or the concentration carbon to halogen. So halogen may be fluorine, chlorine, bromine, bond polar making carbocation, that is C plus. The carbon gets partial positive charge. Carbon gets positive charge, and second halogen gets this is the leaving group that gets partial negative charge, that is halogen, chlorine, bromine and iodine. You observe here the decreasing basicity, increasing stability. Decreasing basicity increasing the stability. See that is the table you observed here. So iodine, iodide ion, bromide ion, and chloride ion, and fluoride ion, and hydroxide ion. So pKb value, by decreasing pKb value, you observe the basicity and increasing stability of cations. Second order nucleophilic substitution reactions, that is SN2 reaction. Here you see second order nucleophilic substitution reaction. See hydroxide ion being attacking to alkyl halide, and transition form we will get methyl alcohol and bromide ion. See there are the rate of SN2 reaction depends upon 4 factors. They are the nature of substrate, that is alkyl halide, the power of the nucleophile, the ability of the leaving group to leave, and the nature of the solvent. In first one, consider the nature of the substrate. So that is unhindered alkyl halide, those in which the backside of the alpha carbon is not blocked will react fastest in SN2 reactions. So that is, methyl, primary methyl, then primary, and then secondary, and then tertiary alkyl halides are favored for SN2 reaction. So while a methyl halides reacts quickly in SN2 reactions, a tertiary does not react. The backside of the alpha carbon in tertiary alkyl halide is completely blocked by major groups, that is they are methyl groups. The effect of nature of substrate on rate of SN2 reaction. See here the nature of substrate. So first one methyl bromide, then ethyl bromide, then isopropyl bromide, and tertiary butyl bromide. See here the space filling model shows actually shapes or relative sizes, means steric hindrance you see here. So in first one, so that is easy, there is no steric hindrance, that's why it is favored for SN2 reaction. So methyl, and then primary, and then secondary, and then tertiary. So this is the order, and then the effect of nucleophile on SN2 reactions. So the alpha carbon in vinyl and aryl halide as a tertiary carbocations is completely hindered, and these alkyl halides do not undergo SN2 reactions. So you see here the vinyl bromide and bromobenzene, they do not undergo SN2 reactions. Why? Because the overlapping p orbitals that are formed, the pi bonds in vinyl and aryl halides completely block the access of nucleophile to the backside of the alpha carbon. So the nature of substrate on rate of SN2 reactions. So consider the power of the nucleophile. So the better the nucleophile, the faster the rate of SN2 reaction. So the table below shows the relative power or power of various nucleophiles. The best nucleophiles are the best electron donors. See here bisulfate and biphosphate and acetic acid. So they are very weak relatively. Their strength is 0.01. So then weak, that is alcohol, water, and nitrate ion. So then fair, which are fair? They are fluoride anion, chloride anion, acetate anion, and ammonia, and dimethyl sulfide. So then good. See, good are bromide, so azide ion N3 minus, so hydroxide ion, and methoxide ion CH3O minus, and then very good cyanide anion, so hydrogen sulfide, then ammonia, and magnesium, alkyl magnesium halide, iodide, and hydride ions. So these are the good. And then consider the nature of the leaving group. So we should consider the leaving group nature also. So groups which best stabilize a negative charge are the best leaving groups. That is, the weakest bases are stable in as way anions and are the best leaving groups. See here, weak base are readily identified. See, they have high pKb values. They are See pKb high value, iodide ion 30,000. So pKb is 23. Then bromide pKb 22 and chloride 21, fluoride 11. pKb value of hydroxide ion is minus 1.7 and alkoxide ion, that is pKb minus 2, and amine ion is minus 21. So the increasing leaving abilities are like this. See, iodine is a good leaving group because iodide is non-basic. The hydroxide group OH minus is a poor leaving group because hydroxide is a strong base. Then effect of the solvent on the rate of SN2 reactions. See, fourth one, consider the nature of solvent. See, here there are three clear classes of organic solvents. We have protic solvents, protic polar solvents, which contains hydroxide or NH2 groups. Protic solvents slow down the SN2 reactions. But polar aprotic solvents like acetone, which contain strong dipoles but no hydroxide or no NH2 groups, polar aprotic solvents speed up the SN2 reaction. So non-polar solvents, example hydrocarbons, SN2 reactions are relatively slow in non-polar solvents. See here, protic solvents, example water, methanol, ethanol, acetic acid, etc. cluster around the nucleus, so that is nucleophile solvent, and lower its energy, stabilize and reduce its reactivity via hydrogen bonding. See here, a solvated anion nucleophile has reduced nucleophilicity, that is, see here, solvated nucleophile has difficulty hitting the alpha carbocation. See the effect of solvent on SN2 reactions, that is, first one acetonitrile, and then here dimethyl, that is acetone, dimethyl ketone, also called as acetone. So polar aprotic solvents solvate the cation counterion of the nucleophile but not the nucleophile. So examples include acetonitrile, acetone, dimethylamide DMF, and dimethyl sulfoxide DMSO, and hexamethylene phosphomide HMPA, and dimethyl acetamide DMA. See, these are the structures of DMF, DMSO, dimethyl formamide, dimethyl sulfoxide, hexamethylene phosphoramide, and dimethylamide. You see the structures, how it is affecting the SN2 reaction. Effect of the solvent on rate of SN2 reactions. So non-polar solvents like benzene, carbon tetrachloride, hexane, cyclohexane do not solvate or stabilize nucleophiles. So SN2 reactions are relatively slow in non-polar solvents, similar to in protic solvents. See benzene, carbon tetrachloride, and N-hexane. So these are do not solvate or stabilize the nucleophiles. So see, solvent effect for SN2 reactions requires polar aprotic solvent. Polar aprotic solvent. No alcohols or no amines. So alcohols or amines are slower the SN2 reactions. Why? Because hydrogen bonding with the nucleophile can occur, slowing down the reaction. See here how the hydrogen bonding is taking place between nucleophile and alcohol and even amine. So their alcohol and amine are not affecting the not favor the SN2 reaction. Yes. So see here polar aprotic solvents. These are the favors SN2 reaction, that is dimethyl sulfoxide, dimethyl formamide, acetonitrile, and hexamethyl phosphomide. So these are the polar aprotic solvents, favors SN2 reaction. And then SN2 conditions summary here. Substrate, that is methyl halide, is better than primary, and then secondary, and then tertiary. Second, nucleophile negative charge is greater than neutral. So leaving group Y stabilizes a negative charge. and solvents needs to be polar and aprotic solvent. Solvent needs to be polar and aprotic solvent. Yes. So now next, that is an SN1 reaction. So the reactions of tertiary butyl chloride with hydroxide ion, you see here. So the reaction of tertiary butyl chloride with hydroxide ion. See here. So this is unimolecular nucleophilic reaction, SN1 reaction. Example, tertiary butyl bromide treated with sodium iodide. This is a rapid reaction, will gives tertiary, that is tertiary methyl iodide and sodium bromide. See here, tertiary alkyl halide. Tertiary alkyl halides are essentially inert to substitution by the SN2 mechanism because of steric hindrance at the backside of the alpha carbon. But despite of this, tertiary alkyl halides undergo nucleophilic substitution reactions quite rapidly, but by a different mechanism, that is the SN1 mechanism. In SN1 mechanism, you see SN1 substitution nucleophilic first order reaction. Here order of reaction is 1. In SN1 reaction, obey first order kinetics, that is rate is directly proportional to the concentration of alkyl halide only. Rate do not depends upon concentration of nucleophile. So the rate depends upon the concentration of only one reactant, that is alkyl halide, not the nucleophile. So the order of reaction of substrates for SN1 reaction is the reverse of SN2. See here, tertiary alkyl halide is more favors than secondary, than primary, than vinyl and phenyl and methyl. See, this is the reverse of SN2, increasing rate of SN1 reactions. Yeah, so see here mechanism of SN1 reactions. So the mechanism of SN1 reaction here occurs in 2 steps. So in first step, carbocation takes place. So the formation of carbocation by leaving of a leaving group, that is halide ion. When it leaves, the intermediate is formed, that is carbocation, is stable little bit than transition state. So the second step is rapid step. Here nucleophile attacked on substrate, that is carbocation, and forms the product, that is tertiary butyl iodide and sodium bromide. See here reaction steps, the slower rate limiting dissociation of the alkyl halide forming carbocation intermediate. So that is rate determining step, slowest step. In slowest step only the alkyl halide is participated. That's why it is a unimolecular substitution reaction. So a rapid nucleophile attack on the carbocation in next step. So note that here nucleophile is not involved in the slower or rate limiting step or rate determining step. See, the rate of SN1 reaction depends upon 3 factors, that is nature of the substrate, that is alkyl halide, and the ability of leaving group, and the nature of the solvent. So rate independent of the power of the nucleophile. Keep it in your mind. Yeah. Next, children, see, consider the nature of the substrate. So highly substituted alkyl halides form more stable carbocations. See, tertiary carbocation is more stable than secondary, than primary, and than methyl. So here tertiary alkyl halide is more favors or for the formation of SN1 reaction. So substrate which is favor tertiary alkyl halide, then secondary, then primary, and then methyl. Yeah, stability of carbocations. This is also one of the factor. Alkyl groups are weak electron donors. Alkyl groups are very weak electron donors. They stabilize carbocations by donating electron density by induction through sigma bonds. See, carbocation here form inductive effect. Alkyl groups donate electrons, density is increases. So sigma bonds to form stabilize the carbocation. So the stabilized carbocations by hyperconjugation, by partial overlap of alkyl carbon to hydrogen bonds with the empty p orbital of the carbocation. Yeah, see here, this is the diagram. Hyperconjugation, how favors the formation of carbocation. sp2 hybridized carbocation. So that is hyperconjugation, vacant p orbital of carbocation, and overlap hyperconjugation. So the sp3 sigma bond orbital second carbon. So this is the hyperconjugation. Next, stability of carbocations. So this is also another factor. Allyl and benzyl halides also react quickly by SN1 reactions because their carbocations are usually stable due to their resonance forms which delocalize charge over an extended pi system. See here, primary allyl carbocation, secondary allyl carbocation. They both are having two different resonance structures. The resonance gives more stability. That's why allyl and benzyl halides both are also react quickly by SN1, but they do not undergo SN2 reaction. See here, the carbocation formed by the benzylic group. See in this, that is the resonance forms of secondary benzyl halide. The relative stability of all types of carbocations, increasing stability and rate of SN1 reaction. See, secondary and primary benzylic, and then tertiary benzylic, secondary benzylic, and then tertiary, and then secondary, and then primary, and then vinyl and phenyl and benzyl. So note that the allylic acid primary benzylic carbocation are about as stable as secondary allyl carbocations. Second, note that secondary allylic carbocations and secondary benzylic carbocations are about to stable as tertiary allyl carbocations. Note that allylic carbocation, tertiary benzylic carbocations are more stable than tertiary allylic carbocations. So these are the stability, relative stability of all types of carbocations. Next, effect of the nucleophile on rate of SN1 reactions. So consider the nature of the nucleophile. So recall again that the nature of the nucleophile has no effect on the rate of SN1 reactions because the slowest rate determining step of an SN1 reaction is the dissociation of the leaving group and formation of the carbocation. So all carbocations are very good electrophiles, so electron acceptors, and even weak nucleophile like H2O and methanol will react quickly with them. So the two SN1 reactions will proceed at essentially the same rate since the only difference is the nucleophile. See here, tertiary butyl bromide treated with sodium iodide, we will get tertiary butyl iodide and sodium bromide. If you take tertiary butyl bromide treated with potassium fluoride, we will get tertiary butyl fluoride and potassium bromide. Yeah, effect of the nature of leaving group on rate of SN1 reaction. So consider the nature of leaving group. The nature of leaving group has the same effect on both SN1 and SN2 reactions. So the better the leaving group, the faster the carbocation form, and hence the faster will be SN1 reaction. So the leaving group usually has a negative charge. So groups which best stabilize a negative charge are the best leaving groups. That is, the weakest bases are stable as anions and are the best leaving groups. See, weak bases are readily identified and they have high pKb values. Already we discussed in previous slide. See, iodine is a good leaving group because iodide is non-basic. The hydroxyl group is a poor leaving group because hydroxide ion is a strong base. See, effect of the solvent on rate of SN1 reaction. Consider the nature of the solvent. See here, for SN1 reaction, the solvent effect, the rate only it is influences the stability of the charged transition state, that is the carbocation. The nucleophile is not involved in the rate determining step. So solvent effects on the nucleophile do not affect the rate of SN1 reactions. So polar solvents, both protic and aprotic, will stabilize the charged transition state but lowering the activation energy and accelerating the SN1 reactions, but non-polar solvents do not lower the activation energy and thus make SN1 reactions relatively slower. So the relative rates of SN1 reaction due to solvent effects are given here. So tertiary butyl chloride reacts with alcohol, it gives tertiary butyl alkyl oxide and HCl. See, water and then ethanol and then ethanol 40%, 20% and normal ethanol. So reaction rate increases with polarity of solvent. So effect of the solvent on SN1 reactions. Solvent polarity is usually expressed by the dielectric constant, which is a measure of the ability of some to act as an electric insulator. So polar solvents are good electric insulators because their dipoles surround and associate with charged spaces. So dielectric constants of some common solvents are given in the lowering the table. See, this is the table. You observe dielectric constant of protic solvents and aprotic solvents. So hexane 1.9, then diethyl ether and chloroform and hexamethyl phosphamide, dimethyl formamide, dimethyl sulfoxide. These are aprotic solvents, and protic solvents acetic acid and acetone, ethanol, methanol, formic acid and water. So these are the structures of solvents. So hexamethyl phosphamide and dimethyl sulfoxide, they are non-polar solvents. So dimethyl formamide, so this is the structure of dimethyl formamide, and see the reactivity of alkyl halides towards substitution reactions. So primary alkyl halide does not occur SN1 reaction, but highly favored for SN2 reaction. The secondary halide can occur under solvolysis conditions in polar solvents, favored by good nucleophiles in polar aprotic solvents, but tertiary alkyl halide favored by the non-basic nucleophiles in polar solvents, but in SN2 tertiary butyl alcohol or tertiary halides does not occur. So effects of reaction variables on substitution and elimination reactions. See here SN1 and SN2 reactions. So solvent very strong effect reaction favored by polar solvents, and SN2 strong effect, that is reaction favored by polar aprotic solvents. So nucleophile weak effect reaction favored poor nucleophile weak base, and strong effect reaction favored by good nucleophile weak base. So leaving group and substrate structure we already discussed. Overall summary of SN1 SN2 reactions. See see here methyl, that is primary and secondary and tertiary alkyl halides, how they favored you observed here.